just as long as I can remember, always fascinated by the weather. And of course, it's the extreme weather that fascinates you. It's not just, a puffy cumulus cloud. It's when shit's going down. Yeah, so I got my undergrad degree at Texas A&M in meteorology. While at A&M, I did an internship at the National Weather Service. Found the forecasting okay, but my very first day went out on a storm survey of an event that was non-tornadic, but caused damage in a small town northwest of Austin, and then started looking at the radar data with that event and really dove into it. And so, ironically, it was my experience in an operational meteorology position that made me fascinated with research. So, at the conclusion of my dissertation, which was almost exclusively a modeling project, I was using cloud resolving simulations to examine the interaction of thunderstorms with air mass boundaries. I realized that if I wanted to complement this with observational work, I needed good observations above the surface and not vertical profiles principally, but horizontal transects, because a lot of the gradients that are important for these boundaries manifest in the horizontal, not the vertical. Moreover, I needed vertical motion. I needed vertical velocity, which a radiosonde is not going to give you. Thought maybe manned aircraft might work, but it just seemed logistically challenging. So this idea of using drones was appealing. So I ended up applying for a Big 12 faculty fellowship back when both CU and UNL were in the Big 12. Got that for basically 2 weeks to go out to Boulder and begin the conversation. And so met with Brian and Jack Elston. We came up with an idea to write a proposal for a small grant for exploratory research to NSF to kind of flesh out this concept, and got that funded. And COCONU, the Collaborative Colorado Nebraska UAS experiment, emerged from that initial set of discussions. About that time, actually, in 2008, we put in a proposal to participate in Vortex 2, which was the second verification of the origins of rotation tornadoes experiment. They funded us as kind of a proof of concept. I think from 2012 on, we were out in the field just doing not really science forward work, but more engineering forward work, trying to get a platform that we were confident worked well and a ConOps that seemed to work well. And finally, in 2018, got funding for TORUS. TORUS is targeted observation by radars and UAS of supercells. TORUS LItE is TORUS, but with a left flank intensive experiment. The overarching question for TORUS was whether or not the internal boundaries and other what we call coherent structures, what role they play in moving a supercell thunderstorm towards creating a tornado. We know that tornadoes typically form at the intersection of these internal boundaries. That's been known for years. What we don't know is whether those boundaries are really fundamentally important for this contraction of rotation to a tornado. Because theoretically, they could just be along for the ride. They have no dynamic, physical, unique connection to tornadogenesis. But there's reason to believe, based on some of the work that I've done, that others have done, that these boundaries are uniquely capable of moving a storm towards becoming tornadic. And so that's what we wanted to try to do. We wanted to try to answer the question, are these boundaries actually essential for tornadogenesis, or if they're just associative? They're just, again, kind of along for the ride. TORUS was partly what I wanted to do when it comes to supercells. It was directly leveraging the progress we made during Vortex 2. It involved people that I'd been talking about this work with, brand new platform. So we'd been using the Twister for a number of years, but decided to go to the Raven, which turned out to be a good platform, but learned a lot in this process. So the Twister was a really nice platform. It could fly really fast, but we were kind of limited on range and time in the sky. Twister was a dual prop. Dual prop freed up the fuselage for instrumentation, but it was kind of a small fuselage, so we're kind of limited both for batteries and avionics and everything else. Um, but I mean, we did have we knew we got good data from it. It was just, I think, more of a practical consideration for the aircraft. It was a long wingspan, kind of hard to launch. In Vortex 2, we were using a ground-based catapult system. So basically, I had the rubber band and the kind of PVC uh, mount, and that was a pain. It worked, but not great. In 17 or 18, we tried a roof launch for the Twister. Um, I hated that from the start because it was not something like the Ravcat now. You actually had to put the aircraft on and then drive, and then it would launch. And the pilot was right there at the point where it would launch off and turn on. It was just clunky. So um, I think the writing was on the wall that that platform was not going to be the platform to use. We needed something smaller. We needed something that could be launched more versatilely. Um, and something with a bigger fuselage. The glider configuration for the Twister and the Tempest was nice, but we felt like we could get more flight time out of a different setup. So, bottom line is the Raven turned out to be a great platform. The Ravcat made launching really straightforward. It was a tough aircraft. We crashed it a bunch, and it still worked really well. We got to a point where sensing the instruments were in a good place and getting decent data. And I think most importantly, the flight time was great. I mean, we're north of 2 hours on our flights, and boy, that just made things so much easier. I mean, there are a lot of times where we were able to land and still had battery power, whereas with the Tempest and Twister, there were times we thought we're not going to make it. This is not going to get to a point where it's safe. Um, so yeah, happy with the engineering performance of the Raven. I think we still have a fundamental problem. I think there are ways to resolve it, but we just couldn't converge on a solution. The beauty of these platforms is that they can crash and no one's killed. I mean, there's nobody in it, right? Let's not forget that that's the purpose of these things. The problem is that the way we have to operate is we have to have a ground-based observer beneath each aircraft. And so when you take these aircraft into the storms, you are taking people into the storms. We're okay being in that position. My vehicles are set up that, yeah, if there's big hail, we're not talking about tornadoes, and we're not taking them into tornadoes. But even taking them into parts of the storm that we want to target, there's big hail there, and it could do damage, certainly to the aircraft, but also to the vehicles. But I mean, I have vehicles that are set up to protect them. It's not foolproof, but at least I feel confident that the people are generally going to be safe. So far, and the analysis is still underway. But one of the things I think we have been able to discern is not something that we were aiming to test with TORUS, but something that I had wanted to test for many years, which is the role of pre-existing air mass boundaries on storms. And I still think there's a lot that we don't understand, but particularly the case on the 28th of May in 2019, one of my students led the analysis of that case. We saw that there was this pre-existing feature that seemed to have an important, profound impact on the storm, leading it to produce a tornado in an environment that wouldn't otherwise have supported tornadoes. And this feature wasn't resolved by the conventional observing network, so it was invisible. But we saw it with our data. But even our data were limited. I mean, so we couldn't track this feature all the way to the storm. It was near the storm, and so we can infer based on the environment that it probably had an impact. We could use radar data along with the in situ data to kind of close that gap in understanding. But I think that was an important contribution, that the role of pre-existing MS boundaries and on storms. And the importance of observations that are very localized around the storm, because it was not observed by the conventional observing network. It was only through the observations that we collected that we saw it. And even the observations, even if there happened to be some conventional observations nearby, it may not have seen it anyway because you had to make observations above the surface to see it. And I think that's one of the importance of these particular types of observations. The structural characteristics of some of these boundaries that we have seen in storms, not pre-existing boundaries, but storm boundaries created by the storms. The detailed structure of them, particularly thermodynamically, has not been shown because you need observations that we not until TORUS really had. And so characterizing these boundaries, again, these internal boundaries, allows us to conceptualize their evolution, their dynamics in a much better way. Because, I mean, it's kind of pithy, but you can't understand what you can't see. And so until we get those data to expose their characteristics, it was impossible to try to conceptualize them. And then with that conceptualization, with a better understanding of the dynamics, then we can start to infer their role in the overall storm behavior. And we're assimilating these data that we collected from TORUS into numerical weather prediction models to see how they might impact the forecast. And we've shown that, at least in one case, there was a decent improvement of another student working on additional cases. So we'd like to see across what will end up being 4 total cases, how those data impact the forecast. And there are other people working, other collaborators doing something similar at the National Severe Storms Lab, but they're mainly focused on how we can build a 3-dimensional picture of the storm using this assimilation process, as opposed to how we can improve the forecast. They're related, but we're really focused on how you can improve the forecast with these data.